So good morning, good afternoon, good evening, depends on where you are in the world. So today we are here to see a very interesting talk by Professor Amlan Chakrabarti from University of Calcutta in India. But before giving the floor to Amlan, I'm going just to do some brief announcements. So next Friday, we have a talk by Professor Robert Will from Technical University of Munich in Germany and also SCCH in Austria. So he's going to talk about the design automation software for quantum computing, how to or not reinvent the wheel. So this will be also another very interesting topic. But if you lost the talks that are being organized since year 2020, there is about 150 talks available in this YouTube channel for free for sure, and with excellent talks. Then next flagship conference of IEEE Security System Society in Latin America, Lascas, will be in Bento Gonçalves. This is the most traditional wine region in the south of Brazil. And as you should know, as a flagship conference of CASS, there is a short path to have also the best papers in TCAS 2. In case of being selected to TCAS 2, the paper will appear in the edition of the months of the conference, and then in the proceedings only the abstract. And during the conference, there is an extra evaluation, and then some papers will be invited for a special issue of TCAS 1, where you can really extend your paper to 11 pages or more if you want to pay extra pages. So this is a great opportunity to come to south of Brazil, and 2026, Lascas will be in Arequipa in Peru, always the last week of February. So another very nice location. In 2027, it goes to Panama City, so also nice as you can see. And April next year in Brazil, the northeast of Brazil, Fortaleza, where there is direct flights to Europe and USA. We are going to do the first edition of the IEEE Latin Conference on Internet of Things. This is a IEEE IoT Technical Community Flagship Conference. So I hope that you will be interested also to come. As you know, the IEEE Technical Community is sponsored by 12 IEEE societies. One of the major sponsors of the IEEE IoT TC is Circuits and Systems Society. So I hope that you are going to submit some paper, and a great opportunity also to exchange your work to people from different domains in different IEEE societies. Then in August this year, we have SBCCI 2024. So the program is already available. It will be in the northeast of Brazil. So this is too late to submit any paper now, but you can consider to prepare your papers for SBCCI 2025. That will be in Manaus, so the gateway to the jungle. So a new edition of the Chip in the Jungle, and this will be also a very nice location to host the conference. So last time we went to Manaus was in year 2000. So we are going to be back 25 years later. And we are celebrating this year 75 years of CASS. And then there is a promotion if you are not member of CASS and you never been, you can be a member in 2024 for free. So this offer is still next August. So that means next month. So don't lose the opportunity to become also a CASS member for free. But we are here today to attend the talk by Professor Amlan Chakrabarti about Industry 4.0 and RISC-V, the future of digital transformation. So Professor Amlan Chakrabarti is the director of the School of Information Technology at in India. He is renowned for his groundbreaking work on cyber physical system, design automation, machine learning, and risk design. A senior member of IEEE and ACM, he has also served as a distinguished speaker for both the IEEE Computer Society and ACM. His pioneering research integrates machine learning with cyber physical systems, driving advancements in automation and intelligent system design. Additionally, his contributions to RISC-V design have established him as a key figure in the open source hardware community, fostering innovation and energy efficient computing solutions. So, thank you very much, Professor Amlan, to accept our invitation. And the floor is with you to start your talk.
Oh, yeah, thank you. Okay, thank you, Professor Ricardo. And thanks to IEEE CASS for inviting me. And okay, we had a long connection with Professor Ricardo. I have met connecting him, I think, for the past 5+ years, and I always find him very inspiring. And so I thought that we discussed in the recent conference of ISVLSI at Knoxville, and I accepted his proposal that I will speak on something which I'm working not very long, though I am working in the domain of cyber physical system for almost 15+ years, worked on multiple projects, government as well as funded by industries. But working in that domain for a long period, I found that this is something which is picking up at a very high pace, and that I will try to discuss today. And my focus will be that to motivate all of you to think of this open source hardware platform, which is the RISC-V, and what are the challenges, and as well as what are the benefits we can get and leverage the RISC-V, right, in multiple applications in industry, and how to think as a sort of how to build this community of open source hardware, right, and have with the RISC-V as one of its great contribution. So let me start my presentation. As already introduced by Professor Ricardo, I am presently the director of School of Information Technology, University of Calcutta, India. The University of Calcutta is the oldest university in our country, India, and it is 170+ years. And I am very privileged to lead the School of Information Technology, which does multiple domains of interdisciplinary research in information technology, computer science, electrical engineering, biomedical engineering, quantum computing, and so on. And so this is my background, and I will wish that all of you should visit India, right, whenever opportunity comes, right, and connect with our university. Okay, so let me start my lecture straight away from here. So what I'm pitching today, and obviously this is not that this is a thing which is just came out, but obviously this motivation and the hard work on generating this open hardware, okay, which leads to the open era of computing, right, is really a motivation, and this motivation is getting a very good shape in the recent years because a lot of ecosystem build-up has been done, and that I will discuss in my lecture today. So we know that open collaboration or open design and development is so important in the present era. Okay, it's not only the cutting off the IP cost, but what gives you the actual thing is the flexibility. Flexibility in terms of design, okay, flexibility in terms of the tools what you use, okay, can be used for multiple open platforms, open hardware platforms, okay. So it gives you, or it leverage a sort of collaboration also, okay, because a lot of people have to work together, okay, to develop this open hardware, because there are a lot of things used to be done, to build this ecosystem. Okay, but as it is open, collaboration is more free. Okay, collaboration is, okay, that means is more free coming, or collaboration is more, okay, very welcoming for all of us. Okay, right. And being an open hardware, it has a lot of flexibility, right? Flexibility in terms of how to stretch the design, how to compress the design, right? How to extend the design, right? How to map the design with your specific application, okay, pretty well on your own terms. Okay, and that flexibility gives you a freedom that, hey, I have a hardware, and that means I have a design and I have the tools, okay, so that we can extend this hardware as per my requirement, okay, right, and can do the purpose of design. Okay, and this gives you a different opportunities in terms of the fabrication coming out of those particular new ways of designing the hardware, chips coming out. Okay, semiconductor industry also gets a little bit different direction, right? So let's try to look into this scenario of what is this risk. Obviously the risk, we know that it's a term, it's an abbreviation. Okay, its full form is reduced instruction set computer. What it means that the instruction set, obviously we know that instruction set architecture is a very primary understanding, okay, of how, okay, we can exploit, okay, the hardware, okay, for different terms, for different types of executions, because the instruction set, okay, gives you the opportunity that what are the exact things you will be doing in the hardware. Okay, so if you tell that it's a reduced instruction set, it means that the instruction set is very optimum. Instruction set consists of, okay, very, very fundamental instructions. Okay, complex instructions are not there, which can be as a complex instruction means that the instruction, though complex in the instruction set level, instruction set level, but it will be ultimately fragmented into multiple branches in the actual execution of the processor in the processor pipeline. Whereas when you take, okay, that is called a complex instruction set computer, or CISC computer. But when we tell it's a RISC computer or a RISC processor, it means that whatever instructions we are putting into my processor, each of the instructions will be executed as such, because they are the most fundamental or primitive instructions what the processor can handle. Okay, so they are called as very, very lightweight instructions also. Okay, so if we see the value chain, right? So what do we have? We normally, the flow from the high level software, from the software application, okay, to the processor, to the execution, okay, at our processor, is being bridged by something called instruction set. Okay, instruction set. And why it's called an instruction set architecture, a processor is called an instruction set architecture, because the processor has the hardware blocks, or more we can say the electronic circuits, okay, which are sufficient to execute, okay, all the instruction on the hardware. Okay, and that's why the purpose of a processor designer is that, hey, whatever components or whatever circuitry I'm putting up in this particular processor will be sufficient to support all the instruction, okay, provided in the instruction set, or the instruction set what I am planning to have for this processor. Okay, right? And the compiler, and what a compiler does, compiler actually gets the input from the high level program and tries to map the high level instruction sequence to a sequence of these low level instructions, or the instructions which are available in the instruction set for the particular processor. So instruction set forms a bridge between the hardware and the processor architecture, the software and the processor and the underlying processor architecture, because with that instructions with the coupling occurs. Okay, coupling between the software sequence of instructions, okay, high level instructions, and then pushed into the actual hardware. So obviously the focus is obviously to design processor chips which can support a specific instruction set. Okay, now let's look into that. What are the things we require for that? Obviously we require a lot of design tools, okay, because we need to have some sort of functional logic of my processor. Okay, once we develop the functional logic of the processor, we have to verify it, right? And once we do it, and then we actually put it in, right, in some sort of test hardware, which can be FPGA, which can be, we can generate the RTL of that particular functional processor, and we can generate the RTL, and then we can place it to an FPGA, or we can actually do the physical layout of that, and we can tape it out as an ASIC. Okay, but whatever we do, we are building our processor chips. Okay, now what happens to these design tools for the processor design? If we look into the proprietary processors, the processors having the proprietary IP, right, they have their own design tools. Okay, right, and the design tool of a proprietary processor or an IP processor, an IP based processor, might not be good, right, or might not be actually might not work if you try to work on another type of processor, another proprietary processor. Okay, because every proprietary processor has a sort of coverage of its IP. Okay, so the tool vendor cannot actually work with multiple of this. Okay, it's difficult. Okay, but whereas being an open IP for a RISC processor, if we look on the figure on the right, we will see that it's a very good use of the tool chain. Okay, which means that you can develop a tool chain, right, and this tool chain can target various different types of open IP based RISC architectures. Okay, different variants of RISC architectures, right, and that helps a very good development of this tool and the processor design effort and the actual variety of processors you can generate, okay, with a particular set of tools. Okay, now if we look into the what I can say, the advantage, right, why one should pitch for the RISC platform. Okay, we know that there are some challenges, okay, or there are some things to be done, okay, which actually involve certain cost, right? And if we try to compare with the legacy ISA means the ISA which are not this open hardware ISA, unlike the RISC-V ISA, okay, the traditional ISAs, right? Obviously the traditional ISAs will have large number of instructions in this instruction set, okay, because most often they are of the type CISC. So if you have complex instructions in the instruction set, okay, you can that means you can generate multiple combinations of the primitive instructions, and you can generate a lot of complex instructions. So the primitive instructions which are there in the RISC, okay, can be combined in various forms, and so multiple complex instructions you can generate. So obviously the number of instructions in a non RISC processor will be much higher, okay, than what we have in the case of RISC, okay. And what can be done in the case of okay, the incremental ISA means that you can, okay, as it is complex, you can just actually minimize a little bit complexity or increase a little bit complexity, and you can generate another type of ISA, another little bit modified ISA. Okay, but when you are trying to enhance the, if you are trying to increase the instruction set of a RISC, it means that you are really adding on a functional module, and that functional module, okay, can support a sort of new type of instructions which you need to add into the instruction set architecture. So what it means in the RISC, if you are really doing a value addition in your hardware, okay, then only you require to actually have some, then the instruction set can be altered. Whereas in the case of okay, in the case of okay, a non-RISC or non-RISC processor, you can, okay, you can just do some incremental modifications and some instruction sets can be updated. Okay, design freedom is okay in the case of, obviously in the case of legacy instruction set, which are non-RISC and non-open source hardware. Okay, obviously the design freedom is less because it's limited by license, right? You cannot actually modify or update the components, right? If you have to really do that, you have to come up with an entirely fresh thought process of the processor so that it can come up as a completely new processor. Okay. Okay, but in the case of RISC, you can go on adding modules to the baseline, and you can have different versions of the RISC in terms of the baseline hardware, and then some modular components added, and you can make it as per the requirement of your application. So your freedom is very high. Okay. Obviously, in the case of the non-RISC, okay, non-RISC and non-open hardware type of processors, you have a license fee, royalty fees, right? In the case of RISC-V, right? Obviously, that means okay, if somebody generates okay, a different, okay, that means some sort of IP out of the RISC-V based on the baseline RISC-V processor with some novel contribution. Obviously, that might be having license, but obviously you are free to use a baseline RISC architecture and try to work on it, right, and without giving a license fee. The design ecosystem, okay, though in the legacy ISA, okay, might be quite okay, right, might be pretty standard. Okay, but in the case of RISC-V also, it is increasing. There are a lot of okay, things are happening, and in a very fast pace. Okay, right, and same is the case of the software ecosystem. A lot of software platforms, design platforms, tools platform, verification platforms, test platforms are growing rapidly. Okay, because designers have understood, industries have understood. Okay, that means this is a good domain where okay, where the drive can be given. Okay, so this also gives you a more or less a similar thing what I discussed in just the previous slide, but just in a more okay, in a more analytical way. So if you try to address the question of design challenge, okay, the design challenge is present-day design challenges, especially in the domain of embedded system, edge computing, cyber physical system, right? How your software and hardware is tightly coupled. Okay, so you don't have much higher budget for anything of your size, of your power, right, of your timing resource, okay, of your timing, right? You don't have much budget, or you don't have much buffer for that. Okay, so to do that, you require a very tightly coupled software and hardware, which means that okay, that the hardware should have the exact pipeline, okay, which is the best or the fittest for the instructions to be executed for a specific application. Okay, so what you need to do, you need to work in the both way. You need to work in the both way that, hey, this software requires only this set of instructions, and then the hardware, okay, is good to go enough, is good to support this set of instructions. So there is a sort of push from both the sides, okay, which means that your hardware and software both needs to be customizable, right? And the option of reconfigurable, okay, which means that that means you can always update and change also as the application grows up. So both this flexibility, right, is available in the RISC architecture. Okay, now obviously that means once we design your platform, hardware and software platform, right, and you come up with your design, right, obviously that means you have to have a strong verification, okay, right, to have its to increase the dependability. That means okay, the design is dependable, design is free of errors, okay, right, and design has trustworthiness. Okay, so to do this, you require environments, and hey, that means the risk environment is also coming up with a lot of tools which can actually offer you both the verification, right, and the trusted execution. Okay, secure and trusted execution, right? You also need to have the proof of security of the platform what you are using. Okay, so obviously you require a sort of certification in terms of that means you have to have a sort of verifiable implementable, right, adaptable, design, which should be equally supported by a set of tool chains, right? So so the way we can do is that one way of assurity I can give to my customer is that, hey, that everything what you get here in my product, right, is designed by my team. Okay, that every portion of the software, and when the software gets into the hardware, the entire pipeline is being designed by my team, and it is verified. It's a completely tested, right, and I offer you a very good guarantee to that. Okay, so right, and the tool chains are there to do that. Okay, so this gives you obviously a sort of strong confidence, to your design, right, to your product, right, so that you can pitch it to your customer. Okay, the other thing is that we know that supply chain is a big issue. Okay, supply chain is a big issue because the ecosystem is very strong coherence exists in the ecosystem. Okay, so this is the tool chain. Okay, this is the processor. This is the set of applications you can target. Okay, now if there is a break in this supply chain, right, how you manage? Okay, how you manage that, because that means your entire all the components of your thing are IP. That means are IP bounded, right? Okay, all the components on your SoC, right, are binded by IP. So now if they are binded by IP, right, you require a very good supply chain, to acquire those IPs, right, and to make the design get to the product level. Okay, right, and this supply chain breakage can happen due to many reasons, right, and many of many of the period of that means of operation and design development, right? It can be political issue, it can be pandemics, right? So risk gives you an opportunity that you grow your own chip. Okay, you grow your own hardware, you grow your, that means your software is there, you grow your own processor without the help of any other supply chain. Okay, because entirely you can do it on your design team, by your design team, provided you have the tools and you have the knowledge in the team. Right, I will not brief this. So if you look into the way this risk, the risk development has taken place over the years, right? Though it is from up to 2021, okay, right? We can obviously accept that the 64-bit platform, okay, all the complex operations like vector operations, okay, different types of advanced components are now there in the RISC. Okay, from the very primitive RISC-V, the RISC-V architecture to now we have a very advanced RISC-V architecture, right? And we have this AI SoC application processors are now getting built up on the RISC platform. Okay, so it is there that there is a constant development and constant drive in the RISC design and development. Okay, so it means that it is showing a good success. It is showing a great success, and people are investing their thought process, their time, their technical expertise to make this domain very enriched, right? And ultimately, industry is getting a value out of it. So if you look into the way we can actually provide a value, okay, out of this risk designs, okay. So scenario one, okay. Scenario one is that obviously we know that, okay, that your microprocessor, which were working for the past many years, okay, for different applications in your industry, okay, has gone out. Okay, that means has crossed their lifetime. Okay, has crossed their span. Okay, but you require a sort of exact operation, okay, to be done. Okay, so that you need not to change too many things, right? If you tell that, oh, that means I will change the processor, you have to bring a new processor, okay, which will have a different type of different processor. So you have to start from very scratch, right? On developing and again pushing your application which was running very good, okay, on this particular processor. Okay, either you have to change your software in the many ways, okay, to accommodate with the hardware. Okay, but in the RISC, what we can do in the RISC, we can actually customize the RISC hardware exactly what was going on in this particular CPU. Okay, customize the RISC platform exactly on the functionality of the CPU, but maybe with a lower power. Okay, but maybe with a more higher speed, right? And that gives you a lot of gain, a lot of gain in this particular process. Okay. Second issue is that obviously how to accommodate something which is coming new. So which is coming new, right? One way is that there are some new changes in the requirement, and you try to fit a processor which exactly maps to your new requirement, but you don't get it. Okay, how you work, because your off-the-shelf processors and proprietary processors are not, either they are less or they are more, okay, than what you require here. Okay, so how do you map this new specification exactly? It would have been easier for you if you would have built your own processor, which is the tagline I'm trying to push. Okay, the tagline is that, can we build our own processor? And if we can build our own processor, then we can exactly build our own processor based on the enhanced requirement, and we can map the design which is there, which is required, and we can do it very soon. And we have a hell lot of tools. Okay, like Codasip is one of the very powerful tool chain which can actually which can help you to enable these designs. Okay, for RISC-V. I will just quickly go through this particular thing, and this is more or less the same thing what I discussed. There are a lot of okay, like many of the proprietary processors or IP based processors have progressed, okay, with years, okay, and a lot of both in terms of the technology developed in that particular processor, right, and what are the applications industry have framed based on those technology innovations. Similarly, it has been worked for RISC also. Okay, so RISC processor has got a lot of technological upgradations over the years, and then it has been well utilized by industry or well adopted by industry on all these technological milestones which RISC have achieved. Okay, now having giving you a sort of a brief overview that what is RISC and how RISC is useful, how RISC is beneficial. Okay, now let us get into take this RISC, right, and leverage it, okay, to the industry 4.0. Okay, and industry 4.0 is a combination of data-driven machines having intelligence serving multiple purpose. Okay, I think if I can summarize, it is like that. Okay, so what this machines done? This machines requires a lot of heterogeneous processing or computing requirements are there. Okay, together with communication. Okay, so communication, distributed computing, right? Maybe the computing load are small, okay, but they are of different types. Okay, they have different footprints at different intervals of time, because these are real industrial processing. Okay, where we have variety of workloads. Okay, and we use different infrastructures like cloud. Okay, we use different types of communication like 5G. Okay, 5G 6G communication interface to carry your data into the different stages of the process, right? And also having a seamless handshaking between all the components of a process, and maybe multiple processes are communicating with each other. Okay, okay, right? And for this we require a lot of computation, lot of simulation. Okay, a lot of visualization of the data of the application scenarios. Okay, the examples are obviously additive manufacturing. Okay, the examples are obviously that means your automated systems for monitoring traffic. Okay, automated vehicle. Okay, right? All this hugely autonomous systems are which can work and which can do the precise. The precision is one of the factor. Rate is one of the factor. Okay, accuracy is one of the factor. Complexity is one of the factor. So it can have, that means it can handle this in a very very well mannered fashion. Okay, And okay, and if we look into the main premises or main pillars, or if we try to say here what is the target of industry 4.0, right? What are the uh, okay, main areas, okay, where industry 4.0 focuses upon is obviously the interoperability. Okay, okay, it is basically hugely driven by the sensors and the data captured through the sensors, because those engages the system with the real world. Okay, systems can engage with the real world environment only through the sensors. Okay, so we have a huge amount of data acquisition from the real world, okay, through these IoT nodes, which have the sensors, right, and the data aggregated by the IoT nodes, okay, uh, right, and these are IoT nodes. Okay, IoT nodes are basically this Internet of Things, which means they are connected, and there is huge amount of data communication which are going. Okay, and interoperability means that you need to have a sort of standardization by which, okay, that means multiple components can seamlessly work together. Okay, uh, right. You need to know what is happening. Okay, it's not that okay machines will do their job and we will be in oblivion, so that if something happens wrong, okay, right, we're out of control. You cannot do that, right? You have to have a predictive, prescriptive type of analytics, okay, to handle this type of scenarios, and you have to be very cautious that the scenarios doesn't go wrong. Okay, because the scenarios go wrong, okay, it's a negative impact on the value chain, right? And it can lead to a lot of risks. Okay, it can lead to okay, risks in terms of damages, right? It can lead to risk in terms of okay, very okay, maybe the risk of human life. Okay, so what do you need to do? You need to be very sure that what needs to be done and what is to be done, okay, right, and how it needs to be done. So we know that digital twins are the best way to analyze, to simulate, to realize, to virtualize, okay, the things which will happen, okay, uh, right, in the digital, that means using our digital okay, data platform, right, and generating different analytics out of it, right? You can actually visualize that what are the things, okay, that means you can actually simulate a real scenario, right? And you can analyze the scenario which lot of okay, lot of variations in the parameters. Okay, okay, right. And obviously, as I said, the decentralized decision is also one of the issue, that it is not that okay, it depends on one particular machines. Okay, several machines work together. Okay, several systems work together to make them work. Okay, right. And we need to have, okay, a very efficient cyber physical systems. Okay, uh, okay, which can connect both with the humans and with the machines, right? And we can make a seamless environment by which the humans are very aware of what machines are doing, and can always have a sort of okay, monitoring or capturing, analyzing what is happening in the real field, what the machines are doing. Okay, so if you look into to manage all these things, okay, right, you require safety. Okay, you require performance. You require the performance to work with a high data volume, okay, with good accuracy. Okay, you require computation at high skills, and you require also a good support of security, because there are lot of communications happening and lot of heterogeneous systems are working with each other. Okay, so now if we see that all the things what we require, okay, requires a sort of at scale computing which can support heterogeneous requirement and which can give me a trustworthiness also, right? And right, and we are very sure that a RISC-V platform can offer it. Okay, right. In the case of proprietary, where you miss out at the first of all is that means it's very difficult to build the heterogeneous type of computing, heterogeneous type of requirement in the industry for environment which with one particular IP, okay, with one particular system design, right? Then what you have to do, you have to integrate multiple subsystems to make your system work or make multiple systems work. And this becomes a very costly affair, not only in terms of acquiring those subsystems in terms of IP, but also validating and verifying this, because this comes from different components from different ecosystems might be. Okay. Whereas if you build it on this particular RISC-V platform, it is a seamless single ecosystem which can support a lot of variability, right, in terms of extension of the components. Okay, and this also gives you a lot of security. Okay, we will see very soon the security infrastructure which are very well placed on this particular RISC-V development platforms. Okay, so as I said, that it is going everywhere. Okay, it is going everywhere, right? Data centers, cloud HPC, automotive, okay, running this AI ML engines, okay, edge computing, telecommunications, consumer IoT devices, because you can use this RISC-V at different forms, at different levels of complexity, right, at different levels of extension of the pipeline. So it can okay, the baseline, right, and its variety of extensions in a very large scale can fit the requirement of multiple computing computing infrastructures. Okay, right. And if we see the way the cloud service provider, because why I'm focusing on cloud, because cloud service is a very obvious service now for the business. Okay, you cannot use many of the things on premise, right? And many of the things, okay, you cannot work in a centralized mode. So you have to go in a distributed mode. You have to collect data from distributed centers, right? And you have to use a system which is always on time. Okay, right? And so cloud is a very important system in that perspective. Okay, and if we see this way this RISC-V ecosystem, okay, has the impact it has created, okay, on this particular to build this cloud ecosystem is obviously fabulous. Okay, so we see that we can have the open models for the RISC-V, okay, which are they're pretty easy to integrate in the cloud platform. Okay, because we know what are there. Everything is known, right? What architecture is there, what component is there. So it's integrating it with a very large resource pool is much easier. Okay. Now, due to this open hardware, the cloud security is also one of the important thing, right? You have to identify that what is the vulnerability footprint of your resources. Not only that, you also have to understand that when the attacker comes on you, okay, how you can, what it is footprint and how it can be mitigated. So to know everything, you have to know that the hardware on which the attacker is trying to attack, right? You can prepare every ammunitions inside the hardware, okay, to mitigate the attacker. So to prepare that, you need to have a very transparent understanding of what is your hardware, okay? And obviously, RISC gives you that particular opportunity, okay? Okay, right? And obviously, this open hardware itself gives you the opportunity to work in, to develop various things out of it, without thinking of, okay, the IP or the licensing cost. So there is a huge amount of variability which can be generated in this particular platform, which is also a very win-win situation in the cloud scenario, because cloud scenario goes with the concept of virtualization, and it offers the resources as required by its client. So you can have a variable pool of resources, okay, based on RISC hardware, okay, be it an IoT platform on cloud, okay, so that you can satisfy a very large number of applications, but you can satisfy, okay, as per requirement, okay, and okay, right, and this impacts have actually taken this RISC-V into leverage this RISC-V, okay, right, into the cloud services, okay, and right, and obviously the RISC-V is now getting into the, okay, different types of hardwares at different scales, okay, okay, because they are they're transparent. So security is a very well understood and analyzed and mitigated on those hardware, right? And obviously, right, it generates the opportunity, a lot of innovations, okay, due to its open hardware nature. So not getting into details of this, but if you see that there are a lot of things into this RISC architecture which are already being implemented, already being in practice, from memory safety, okay, from control flow integrity, exception handling, access control, PUF, secure booting, trusted execution environments, okay, which are very essential properties to have, right, to make your hardware, okay, very safe and secure, okay, and this developments in terms of safety and security on the RISC platform, okay, right, are very, okay, well established. So now I come to this particular time where I have almost okay, discussed about the okay, the things what are driving the RISC towards industry, right, and what are the things industry can leverage out of the RISC. And now I will come to the another part where I'm introducing one of the collaborations where, okay, we are having in the RISC-V, which is called an R5. Obviously, R5 adopts the name from the name of RISC-V. This is a startup in India, okay, that means office in Bangalore. Their R&D office in Bangalore, and our University of Calcutta, that's my group of University of Calcutta is working with this for the past almost 1 year, right? And we are trying to, okay, because whatever I have seen, right, I have said today, right, is obviously in knowledge, but we have to bring the knowledge to practice. It is not the RISC-V knowledge which will help industry, but it will the RISC-V practice which will help industry. So we have to have the engineers who can practice RISC-V, and to do that, you need to do a massive level of skill development. Okay, so we are trying to focus on an ecosystem. Obviously, we know India is a large country. India produces, Indian academic institutes produce a lot of engineering talents, engineering students, but we need to nurture them, and we need to actually motivate them, okay, in this particular design practice, right? And then industry can get a lot of help, and industry can actually generate a lot of outcomes out of these activities, okay? RISC-V activity. So that I'm not getting into details of this, but we are trying to make a cycle of this. That means a particular way to build a workforce where we will have the students trained, right, and then they go into the practice, into the community, developing small things from the community, and making their knowledge much more towards the working level, right, and then we will be taking industries, some of the industries which have already shown a support for this activity, like Thales, like our defense, DRDO, like Mahindra, CSI National Aeronautics Limited. They have shown interest on this activity, and we are trying to make this from the development of manpower to actually real practice. And obviously if you see that what is the IP development proposition, how we can generate better value proposition through this development, open hardware based design development is something vis-a-vis of the shelf components. We know that there is a that means effort is to cost efficiency, we have to balance, we have to build a team, we have to generate the low cost IPs, because they're open source based, right, and we can also have the FPGA based implementations, because they are because these are IPs which are open source, so we can actually implement them on FPGA as per our will, and we can actually reduce minimize the supply chain issues with a faster production, right? And we are also proposing that this is especially we are working in India, but obviously it's an international forum, I know, right? A lot of researchers, a lot of industries from South America, from Europe, from Asia, from US, from Southeast Asia might be connected in this particular lecture, right? So this is on the India platform, because in India we have the government of India, that means is actually supporting the Make in India program, where we are trying to have the hardware built in India, right, and try to help the Indian industry, right, and different types of support mechanisms itself of the government, but obviously, and they're providing incentive scheme, they're providing some sort of ecosystem, right, and trying to promote this particular in the domestic and global markets. But obviously the pitch here is that, where I will try to end, is that obviously this is not only the thing what we are doing in India. We require collaborations across the world. Our university team, the R5, which is also working with us, and obviously we want to connect with the other teams across the world who are doing in this RISC-V, right? And we can obviously look forward to a more activity across the world and more collaboration across the world in this particular development. So I end up here, and now open to any questions.
So thank you very much, Amlan, for the very nice talk. So we have here one question from Yuri Vargas. He's a student at UFRGS Brazil. So his question is, what are the resources that RISC-V have in AI SoC right now? And would it be viable to use a RISC-V processor as a controller of a neural network module implemented in hardware?
Yeah, excellent. So what we have
also says that I mean, would it be viable to replace general processors and GPUs in the use of neural networks and use a DNN hardware, the accelerated module controlled by a RISC-V.
Yeah, I think that means I will say the exact research what we are doing with our five is the second point what you rightly mentioned. Okay, so this is our pitch that we are trying to develop the neural accelerators. Controlled by RISC-V. Okay, and we are trying to add the vector processing unit. Okay, on the RISC-V, as you know that most of the neural computations are vector computing, right, or tensor computing. Okay, so we are trying to integrate, okay, those in the RISC pipeline, and trying to extend the RISC pipeline for neural computing. Okay, right. Hopefully within a few months, right, we will be able to come out with some good results, right, and hopefully that means the direction what you have rightly thought about is the right direction where the research is going on.
Okay, thank you. So I see no other question here in the chat channel. If you have a question, please do it now. So I have one. Can you say something about the use of super processors composed by a large network of RISC-Vs?
So that means I haven't worked on that particular system. Okay, but I think that what okay, that means this cluster of processors. Okay, cluster of processors, obviously works, okay, in the scenario, but but we need to have the software stack built on it. Okay, so when we tell it's a super processor, means either we are doing a heavily multi-threading, okay, from the top level of application, or we are using a very heavily memory computation. Okay, it's a large amount of data, okay, in the memory which we need to compute. Okay, so we are not doing this super processor, but we are working with our other part of the work in our research group is also developing scheduler. Okay, right. Okay, that means okay. I didn't mention this for the first question. I should have mentioned this. Okay. So in our lab, we are also building compilers, which can take a GPU program, GPU code, and it can generate the code for the RISC. Okay, and now you can tell that how does it help. It doesn't help that if it is a baseline RISC. Okay, but provided we can advance the RISC, okay, with some vector processing, then probably we can have a notion that hey, look into this algorithm, right, and try to port it into this RISC, right, and vis-a-vis GPU, and you can have a comparison, and probably because what happens in the case of GPU, you always request a host processor to do it. Okay, because you require that means you cannot do the entire computation, okay, in a one single thread. Okay, you have to do multiple GPU threads, and then they have to again synchronize and come back to the host, and then you can get the result out of it. But probably the distribution and branching time might get reduced. Okay, in the case of the pipeline having vector processing unit in this way. That is the first answer of the question. And then for the super processor, yes, that super processor, obviously the scheduling, the memory partitioning, and the threading, okay, needs to be well explored. Okay, but there are promises. There are promises that instead of making a very large costly processor, why not we make some smaller RISC cores and try to make a super processor and try to integrate it with the memory and the top layer threading, right, and try to get the same performance. Yeah, but this we are not doing at present. But there is a lot of work going on. Yes, sure.
Okay, thank you. So we have here now a question by Professor Altamiro Suzin from UFRGS Brazil. Thanks for the presentation. Do we need to have some concerns on legacy of systems when ISA extensions are developed?
This is also a very good question. Okay, so uh, yeah, so I will see that whether it is a concern or it is a need that we need to debate. Okay, okay. First of all, so because the thing is that when we are, so why we don't get out of the legacy system, basically for the functionality. Okay, but we know that legacy system is not giving us that performance, but still we don't take out the legacy system because we are very full belief of the functional accuracy what it is doing. And when I bring in the new system, okay, the challenge is that whether it will give the same functionality, but we are almost very sure that performance in terms of power and timing will be pretty high. So what I mean to say is that, okay, that means it is far easier. Like I'm not telling it has to be I'm not comparing. I'm not giving a specific case also, but I'm trying to say it is far much easier to actually develop a RISC, okay, for a legacy system, okay, right, and try to verify it because it's very transparent. Try to verify it against the application scenario, right, and then can put it, okay, and obviously that makes a better replacement of a legacy system than any other platform. Okay, because if you are trying to use any other platform which is coming proprietary, right, you cannot overlap and you cannot actually map in that way because they may be of two different ways. Okay.
Yeah,
Yeah,
Professor Suzin also is adding that his concern is mainly when cross teams exchange occurs.
yeah. So this is true. This is true when we have this type of okay, cross cross flow. Uh, okay, right, and this uh, okay, this is a challenge. This is a challenge. I think more for the proprietary IPs. Okay, it's a challenge. What I feel, because proprietary IPs have a more challenge towards the cross. Okay. Whereas in case of this open source hardware, right, you know that what this guy is doing, because these also having open source, and what the other guy is also having, right, and to interface them, I think much easier. Yeah.
Thank you very much, Professor Amlan. I see no more questions here in the chat. So thank you very much for your very interesting talk. And then I would like to remind all you that next week we have another CASS talk by Professor Robert Will from Technical University of Munich, Germany, and he's going to talk about the design automation software for quantum computing, how to or not reinvent the wheel. So I hope to see you all next week, and please invite your colleagues also to attend the talks in real time. And so thank you again, Alam, and have you all a nice weekend, and see you next Friday.